Welcome to part 2 of this lecture on path tracing. Today we will talk about importance sampling to make the path tracer from part 1 converge more quickly. As a reminder, last week we learned about the rendering equation, which requires us to compute an integral over 3 factors: incoming radiance, BRDF, and geometry term. And that models how light propagates in a real scene. And then to solve this, we learned about path tracing. So that means we start constructing paths at the camera, and we trace rays and get path vertices. And then to compute the outgoing radiance at each path vertex, we use a Monte Carlo estimate with one random direction sample. And that helps us to estimate the integral in the rendering equation. And by doing this recursively, we construct a path. And then with this path tracer, we got results like this, which actually look quite compelling. At one sample per pixel, it's still quite noisy, but it's not all that bad. However, with this simple path tracer, we still have very serious failure cases. This is the same scene at night, and then you can see that at one sample per pixel, this is extremely noisy. The problem here is that currently we are basically sampling these images here uniformly at random. And then when we have this scene at night, it's very unlikely that one of the random samples that we place here will hit one of these light sources. The light sources are small compared to everything else, so there is only a small chance that we get one of these very bright samples from a light source, and that simply manifests as noise. That is why the image I showed you just now looked that noisy. It would be nice if we could somehow enforce that we can generate more samples towards the light sources, and in general that we generate bright samples more frequently. And that's what importance sampling is about. To convey the basic idea, let's look at this 1D example from last week again. The idea is that we want to sample regions where this function takes large values more frequently. And we can't do this perfectly, but we do have some knowledge about this function. For example, we may know that the function has this discontinuity here at 0.2, and we may suspect that it has larger values to the left of this discontinuity. So what we will do now for this example is that we place samples here to the left of this discontinuity with double density compared to everything to the right. And then, of course, we can't just do this and expect our estimate to still be unbiased. So we have to compensate for this sample distribution. And to do so, we use half the weight for all of these samples to the left. And then we'll see that this is still an unbiased estimate. So this is the basic idea. Now let's make this a bit more formal. First, we have to think about how we can describe the distribution of our samples. And we do this using a probability density function, P of x. For short, this is PDF, but I'll mostly just say density. This is a non-negative function. It can't take negative values, but it can take arbitrarily large values. And then we can take samples proportional to this density. And what that means is that when we look at one of these samples and we look at some interval from C to D, then the probability that our sample is within this interval is exactly the integral over this interval of our probability density function. And of course, the probability that a sample is anywhere in our domain is 100%. So that also gives us a normalization constraint for our densities. if we integrate them over their entire domain, the integral has to be exactly 1. And now our importance sampling Monte Carlo estimate looks like this. It's in principle similar to what we learned last week. It's an average across all of our samples, but now we are dividing the sample values by the corresponding densities. And this is then still an unbiased Monte Carlo estimate as long as one condition is satisfied. This condition is that wherever our function f is non-zero, the density has to be positive. If this were violated, then there would be regions where the function is not 0, but our density is 0, so we have 0 probability to produce samples in these regions, and that means we will never even look at the function value in these regions, and thus we would clearly have a biased estimate. So that's why we need the density to be positive wherever the function is non-zero. Now, the nice thing about this is that we can do this with any density, and with the one that I've used here, you can already see that the variation in our function has diminished a bit, because this used to be much bigger, and now that we have divided out the density, all of the values that we are getting here are a bit closer together, and thus we have less variation in our samples, which means less noise. Of course, we can use another density now, which is even more similar to our integrand f. And then if we use, for example, this one, which I handcrafted for this particular example, then this quotient f over p will look like this. Now you can see that it's actually reasonably close to being constant. The values here don't change all that much anymore, and thus we have even lower variance. If you think this through to the end, then it's obvious what you should be doing. You should be using a density that's exactly proportional to the integrand. So p of x is f of x times some constant factor w. And if we have that, then we can look at this ratio of f over p. And of course, p is now just w times f, so we can put this in here. And then we can cancel f from this and get 1 over w. And now this is constant, so that means we have no noise at all. All of our samples will simply give us the same value and we don't have any variance. But this sounds too good to be true, and indeed there's a problem with this idea. The problem is that our density has to be normalized. So this integral here has to be 1. And then if we put in the definition of p, then it's this. And if we solve this equation, we find that 1 over w is the integral that we wanted to compute. So then it makes sense that this comes out here. Our Monte Carlo estimate is simply the integral, no matter what the random numbers say. But of course, if we can already compute the integral, then we do not need Monte Carlo integration to compute the integral. So in principle, it's possible to have this perfect importance sampling, but it's only possible in cases where you do not need Monte Carlo integration, and then you do not need importance sampling either. And because of that, the challenge with importance sampling is that you have to come up with a density that's simple enough for you to figure out how to sample from this density, but it should still be a reasonably good approximation for the integrand. So for example, this density here is simpler than the integrand, and I would be able to implement a sampling procedure for this, but it's not a perfect fit, so it will reduce the variance, but not to 0. Speaking of sampling procedures, how do we actually generate samples proportional to a given density? For that, we are going to use inverse CDF sampling. Our goal here is to take uniform random numbers in the interval from 0 to 1, and then we want to convert these into random numbers x that are distributed with density p of x. So we can, of course, always get these uniform random numbers in the unit interval easily using, for example, PCG2D. That's the pseudo-random number generator we looked at last week. And our goal is to convert that into samples with the desired density. And to do so, the first step is that we compute the cumulative distribution function, CDF for short, of our density. So that means we are simply taking the integral from the beginning of the domain to x, and that gives us the CDF at x. Then this is what that looks like for this density. So you can see here we have large values in the density and the CDF is growing quite quickly. Here we have smaller values, so it's not growing as quickly. So the CDF is the integral of the density, and vice versa, the density is the derivative of the CDF. And now I claim that if we want to achieve our goal of generating samples x distributed with density p of x, then we can do this by simply putting uniform random numbers u in the interval from 0 to 1 into the inverse of the CDF. And let me explain why I claim that this works. I will also show you a proper proof in a second, but for now let's look at it geometrically. So what we do is we place our uniform random numbers here on the y-axis because they correspond to values of the CDF within this formula. And then we are interested in the result of putting this into the inverse CDF. So what we do is we project these samples along horizontal lines onto our graph of the CDF. And then we project that down to the x-axis. And that exactly gives us the result. This is how you can geometrically think about inverse functions, because the function itself takes you from the x-axis across the graph to the y-axis. And if we go the other way around, that's the inverse function. And now you can already kind of see that these samples have the desired density. So you can see that they are quite dense here and less dense here. But it becomes even more obvious when I replace these random numbers by equidistant samples. So now here these are all equally spaced. And you can now very clearly see that we have a high density here, lower density here, lower density here, moderately high density here. So it's exactly what we wanted. And it works out like that in general. Here is a proper proof of that. The only simplifying assumption that I use is that the density is positive everywhere. It still works if the density is 0 in places where the integrand is also 0, but it does introduce a few technicalities. So the first step in this proof is that we think about the derivative of the inverse CDF. And there's a rule for how to compute the derivative of an inverse function. And the way this works is that you take the reciprocal of the derivative of the function itself and you evaluate that at the point that you get when you put your parameter here into the inverse function. And of course the derivative of the CDF is simply the density. So we now have this equation to describe this derivative here. And now we look at the function that we use in the Monte Carlo estimate. We have f over p because we are using importance sampling, and we are evaluating that at x, and x is what we get when we put a uniform random number into the inverse CDF. So if everything is correct, this integral here should be the integral that we want to compute. And then we can use the rule for the derivative here that we derived just now and replace this by the derivative of the inverse CDF. And with that, we have got something that allows us to use integration by substitution. We have the function, the inverse CDF here, and then here we have the derivative of that. So we can use integration by substitution, and then all that remains is f of x, and we are integrating this from we are integrating this across the domain that's the image of the inverse CDF. So really, since our density is positive everywhere, this is simply the interval from a to b. And with that, we have the integral that we wanted to compute. So what we are actually computing with our Monte Carlo estimate is the integral that we wanted to compute, and that means our importance sampling is correct. Okay, so now we know how importance sampling works in principle, and now we want to apply this to the rendering equation. So we want to improve our path tracer by using importance sampling. And we have three factors for which we could use it, and one of those can sometimes be very simple. If we have a diffuse BRDF, then the BRDF is just constant. So then the geometry term here is one of the more challenging factors, and that's why we will start with this. And a nice thing to use in this context is that the geometry term is exactly the cosine of theta I. So if we take the dot product of the normal vector and this incoming light direction, that's exactly the cosine of the angle between these two normalized vectors, and we will be using this to derive an importance sampling strategy for this geometry term. And all of this will be subsumed under the term of BRDF importance sampling. So let's think about what we did last week. Last week we were generating the inclination angle theta uniformly at random with a density of 2 over pi. And that means that the density that we got in terms of the direction vectors was 1 over pi squared times sine of theta. This pi squared and sine of theta, these are things that showed up in our Monte Carlo estimates last week. And they showed up in these estimates because we had a non-uniform density and we had to compensate for that. So that's a different way of interpreting what we derived last week. And if you look at these samples, you can also see this here. We have sort of a cluster of samples up here at the North Pole. These samples are more dense here than everywhere else because sine of theta approaches 0, and then that means that our density becomes extremely high here. Now what we want to do is to use so-called projected solid angle sampling. That means that we sample proportional to this geometry term with a factor of proportionality or normalization factor W prime that has yet to be determined. And in terms of theta, that means that we are sampling proportional to sine of theta and cosine of theta. Cosine of theta because that corresponds to the geometry term, and sine of theta because we have to compensate for the distortion that we get when we are using spherical coordinates. And then these are the samples that we get, and you can see that we have fewer samples down here close to the horizon because that's where cosine of theta becomes 0. And you can also see that we no longer have this clustering at the North Pole, so that's an improvement. And another interesting observation to make here is that you look at this from the top. So basically we are only looking at the x and y coordinates of this direction vector now. Then this looks uniform, and actually you can prove that these samples here are uniform samples. This is known as the Nusselt analog, and this can be sometimes quite useful when you want to reason about projected solid angles. And in fact, this is also the reason why projected solid angles are called projected solid angles. And I'll explain a bit later what solid angle actually means. Now we want to derive this projected solid angle sampling. So we want to sample this inclination angle theta from 0 to pi over 2 with a density that's proportional to cosine times sine of theta. To do so, we use inverse CDF sampling, and for that we first have to compute the CDF, and then that's an integral over the density. We can put in our definition of the density here, and then integrating over cosine times sine is relatively easy. You can ask a computer algebra system what the integral of that is, and it will have no trouble telling you that it's minus 1/2 over cosine squared of theta. And then this is the CDF that we get. And now that we have this, we can also figure out this normalization factor W, because we want this to be exactly 1 when we put in pi over 2, because this is as far as we want to integrate. And then if we use this formula for the CDF, it works out to this. And since cosine of pi over 2 is simply 0, this has then the solution that W should be exactly 0, because W over 2 should be 1. So the W over 2 here is simply 1, and that means our CDF with proper normalization is this function. And now we have to compute the inverse CDF. So we want to compute a theta that satisfies this equation. And then we put in our definition of the CDF here, and we can take the 1 minus over to the other side. So we have 1 minus u is cosine squared of theta. And then here we first take a square root on both sides, and then we apply the arcus cosine, which is the inverse function of the cosine. And then our final solution is theta equals arcus cosine of square root of 1 minus u. Now we can simplify these formulas a bit. So the first thing that's quite easy to do is, in the end, we only care about cosine of theta, because that's what we need when we compute a direction vector. And cosine of arcus cosine is, of course, the identity function, because these are inverse functions of each other. So we simply have square root of 1 minus u here. And if we want sine of theta, we have sine of arcus cosine. And for that, there's a handy rule, namely you can take the square root of 1 minus the argument squared. And then here we have a square root squared, so this is simply 1 minus u, and then the 1 minus here goes away. So in the end we only have square root of u, which is a very simple result. And now we can put this all together. We want to compute our direction vector omega using spherical coordinates. So we have cosine of phi and sine of theta, and cosine of theta and sine of phi. And phi can be computed as before in our first sampling strategy. So we use 2 pi times ux minus pi, and that gives us a uniform phi ranging from minus pi to pi, which is exactly what we need. And then for sine of theta and cosine of theta, we have derived formulas just now, and we are simply using those here. And then we still have to figure out the normalization factor for our density, but in principle our Monte Carlo estimate now is going to be this. We take f divided by p, And we have a way to compute the direction vector from two uniform random numbers using these formulas here. And the normalization for the density is quite similar to what we had before. So we want to have an integral over the entire hemisphere that comes out to 1. And then this integral, if we express it in terms of spherical coordinates, we need this sine theta factor here again. And we are integrating over the density. And then this integral here is basically cosine of theta times sine of theta. So we can use the formulas derived on the previous slide, and in particular we can reuse the CDF from the previous slide. And then we have f of pi over 2, because here we are integrating up to pi over 2. And this is exactly 1, because we had already normalized this. And then the whole integral, when we have just w prime over 2 integrated from minus pi to pi, comes out to pi times w prime. So what this means is our normalization factor is 1 over pi, and we can use this here. And that's the density that we are sampling with now. Okay, so with that, projected solid angle sampling is complete. That's available to us now, and we can look at its results. The image here to the left is rendered using uniform theta and phi, as we did last week. And here to the right, we have projected solid angle sampling. Now we can look at this up close, and you can see that if you compare the two, we do have more noise here to the left than to the right at the same sample count. So admittedly, this is not a huge improvement, but it's a fairly consistent improvement, and the projected solid angle sampling is not more expensive than what we did last week. So we have no additional cost, but a higher quality, which is of course nice. Okay, with this first success, we now want to move on to other factors that we have in the integrand of the rendering equation. And our next goal will be to deal with specular BRDFs properly. So our goal now is to sample proportional to the product of a specular BRDF and the geometry term. We want to handle both of these at the same time. And this is a bit more complicated than what I explained before. So I won't explain this in detail, but I do want to point you to the solution and illustrate it a bit. The original method was proposed in this paper, and then there were two papers making it more efficient for probably the most relevant case these days, namely for GGX-based BRDFs. This is a very commonly used class of specular BRDFs. And you can see such a BRDF down here. I can adjust the roughness. So large roughness means that it becomes more uniform. Small roughness means that we get an almost mirror-like specular lobe, which is almost just a single point. And depending on the outgoing light direction, this specular highlight moves around. And now we can sample proportional to this BRDF, or almost exactly proportional to it, and we are also counting for the cosine factor or geometry term. And so these samples have been produced with the method described here, and you can see how they pull together when we have a low roughness, how they spread apart when we have a high roughness, how they follow the specular highlight when it moves around. So this method very reliably gives us samples that nicely sample our specular highlight. With that, we now have two sampling strategies, one for diffuse, one for specular, and in many cases we have surfaces that combine both a diffuse material and a specular material, and then we have to combine these two sampling strategies. But we only want to use one sample, so somehow we have to come up with a way to make one sample that uses 2 strategies, or in general M strategies. To do so, we assign an importance to every one of these strategies. This is simply some positive number. And of course, we also know the density for each of the sampling strategies. Then we can compute the total importance, which is simply the sum of the individual importance values. And then we want to pick one of the sampling strategies with index j with a probability that is Cj divided by capital C. So this is the importance of this sampling strategy divided by the total importance. And doing this is not too difficult. The way we do it is that we take one uniform random number, u, in the interval from 0 to 1, and then we multiply this by the total importance. So we get this point up here on this line from 0 to C. And then down here we have lined up all of our sampling strategies. And we have associated each of those with an interval that's exactly as long as the importance of this sampling strategy. And so since our value Cu is uniform up here on this interval, we can now simply select the technique that is below this value Cu. And then this is the technique that we will be using. And since the length of these intervals is proportional to the probabilities that we want, this will give us the desired probabilities. To implement this, we simply perform a linear search for an index j such that the sum up to j minus 1 of the importance values is still less than C times u. But if we include Cj in the sum, then that's bigger. And with that, we find this interval, and then we have selected our sampling strategy. And if we do this, we are combining all of these densities effectively into a single density, and the single density is this one. We are multiplying each probability density function by its respective importance, and then we divide by the total importance. And then we can use this density for importance sampling, so this is what we divide by in the end. And with that, we have a combined sampling strategy. When we want to combine diffuse and specular sampling, then we need to make up our mind what the probability should be to use projected solid angle sampling, or diffuse sampling, same thing. And what I did here in my path tracer is that I'm setting this probability to be the diffuse albedo, but at most 50%. So whichever one of these is smaller, that's the probability for diffuse sampling. And otherwise we use specular sampling. And the reason why I decided to do it like this is that when you have a specular highlight, the specular component is going to be extremely important. So I don't want to be sampling this too seldomly, and that's why I have this limit of 50% here. But honestly, I haven't experimented with that all that much, so other strategies may be better. Nonetheless, let's take a look at the results of this strategy. First of all, I want to show you what we had before using only projected solid angle sampling. And what you can see here is that when we have mirror reflections, such as here, this is quite noisy. If I show it with just one sample per pixel, you can see that this is really noisy. However, when I now transition to using the combined sampling strategy, which also uses specular sampling, it's much better. This mirror reflection here is basically perfect already at one sample per pixel. And this also works in other parts of this scene. For example, here in these windows, even at one sample per pixel, the reflection looks very nice. Okay, that completes our discussion of BRDF importance sampling, and next I want to talk about importance sampling of light sources. To motivate this, let's look at our test scene again, and this is the daytime version of it, rendered with 16 samples per pixel, which looks quite nice. And this is using BRDF sampling. However, when it's nighttime, so the sky isn't as bright, but I've turned on all the street lamps here, then using only BRDF sampling gives us an extremely noisy result. We've seen this before. And if I combine BRDF and light sampling, then the result at the same sample count is much, much better. And the reason for that, as explained before, is that when we do not incorporate knowledge about where the light sources are, then we have a very low probability of hitting one of these light sources with a random ray. And that means seldomly we are lucky and get a very bright sample, but most of the time we don't. And that's always a bad thing in path tracing. You do not want to need luck to get a good sample. You want to use importance sampling to make that the likely outcome. So we will now figure out how to sample directly incoming radiance from light sources. And in the scenes that I've shown you, this is comparatively simple because all the light sources that I have put into these scenes are spherical lights. They are simply spheres which emit light equally into all directions from their entire surface. So here we have such a spherical light. It has a center point C and a radius R. We know both of these. And now we choose a convenient coordinate frame for our computations. We pretend that the shading point or the path vertex xj is the origin of our coordinate frame, and also that this center coordinate of the sphere is on the z-axis. And then what we are interested in now is the set of directions that we have to sample to get directions that point towards this light source. So we want to know the opening angle that we have here for this cone pointing towards the light. And then this set here on the unit sphere is a so-called spherical cap. And to compute this angle, we use trigonometry. So we look at this right triangle here made up of a tangent line to the sphere and the vector towards the center. And then we have this orthogonal line here with the radius. And then trigonometry tells us that the sine of this angle alpha is the quotient of the opposite, which is the radius, and the hypotenuse, which is the length of the vector towards the center. So we have this equation, and then of course we can use the arcus sign on both sides, and then we have alpha equals arcsin of r over length of c. And with that we can compute the opening angle for our spherical cap, and we now want to sample direction vectors within this angle around the z-axis, so within the spherical cap. To do this, we use inverse CDF sampling once again. This will be a similar computation to what we saw before, and I will go over it a bit more quickly. So we want to sample proportional to sine of theta, such that our sampled directions will be uniform on the hemisphere. But we only want to sample within this interval from 0 to alpha. Then we compute the CDF, which is essentially just an integral over sine of theta. So the integral is then minus cosine of theta. And then this is our definite integral here. This is the CDF. Then we compute the normalization factor, which means W times 1 minus cosine of alpha has to be 1. So W is 1 over 1 minus cosine of alpha. And now we solve to get the inverse CDF. So we have, if we multiply 1 minus cosine of alpha over to the other side, then we have this equation. And now we also take the 1 minus to the other side and apply the arcus cosine on both sides. And then we have theta is arcus cosine of 1 minus, and then in parentheses 1 minus of cosine of alpha times u. And that's how we can compute the inclination of our sample. Once again, we want to simplify the expressions that come up here a little bit before we use them. So we need cosine of alpha, and then here we have cosine of arcsin. We saw that before and saw that we can instead take square root of 1 minus this squared. Then here we have cosine of theta for the z-coordinate of our direction vector, but since this is defined in terms of an arcus cosine, we can cancel this and just are left with this. And then sine of theta is always square root of 1 minus omega z squared. Putting this all together, we get our sampling strategy. So here we are computing cosine of alpha, and I call this z min because it's the smallest z-coordinate that we will be generating for our samples. And we derived this on the previous slide. And then we compute the z-coordinate of our sample and then the other two coordinates, and with that we are done. And the density that we get here is 1 over 2 pi times 1 minus z min. And this thing here in the denominator is actually an interesting quantity to look at by itself. It's the so-called solid angle of the spherical cap. So now I'm at the point where I actually tell you what solid angle means. The solid angle of a shape is the area of this shape that remains when we project the shape onto the unit sphere. So for example, for our spherical light, we took the spherical light and we projected it onto the unit sphere, and then we computed the area of this shape on the unit sphere, and that's the solid angle. Now we have a sampling strategy to use for one single spherical light source, but of course our scene has more than one light source, so we again have to combine different sampling strategies. We have one sampling strategy for each light source, each one with its own density, and we combine those in the same way as we saw before when we combined diffuse and specular sampling strategies. The only thing we have to make up our mind about is what we want to use as an importance. And the importance that I decided to use in my renderer is the solid angle of the light source. We just saw how to compute this, multiplied by the emitted radiance of the light, which is constant across its surface. And this is when the light source is above the horizon. But of course it may happen that the light source is completely in the lower hemisphere. And if that's the case, then we already know that our samples will be useless because they will be samples in the lower hemisphere, and that means they have zero contribution because we do not use transparent surfaces in this renderer. So in this case, we want to set the importance to 0. And we can figure out whether this case is present using this simple inequality here. The dot product of the center vector and the normal vector is less than minus the radius of the light source. With that, we have a combined sampling strategy for all the light sources in our scene. Of course, the way I decided to do this here incurs computation for every single path vertex and for every single light. This doesn't scale very well, but I've shown you the quality improvement that we get with this important sampling strategy. It's very significant. So this justifies this cost, at least for the scenes that I am using here for my tests, which have around 30 lights. The key thing is that with the path tracer as is, the compute units are actually very much underutilized. The bottleneck here are actually the ray tracing cores, so having additional computation doesn't cost us anything. So that's why I decided to do it like this, but at the very end I'll also briefly talk about how you can handle larger numbers of light sources efficiently. And of course, you may also want to handle other types of light sources, other light shapes. And similar algorithms exist for all kinds of light sources. Spherical light sources are the easiest case, but if you, for example, have polygons, then there's a method in this paper to do solid angle sampling for those. There's also a specialized method for rectangles, which is a bit more efficient. And if you want even better sampling, then you can use projected solid angle sampling that only generates samples pointing towards the light source. This is available for spheres, polygons, and thin cylinders. And of course, this will take a bit more compute than just the solid angle sampling, but it will give you still higher quality samples. And I should admit here that these are all papers that I wrote myself, so I'm kind of advertising here. Now we have sampling strategies for the BRDF, and we have light sampling, and the last thing we have to do is to combine both of these in a good way. For that, we will be using multiple importance sampling, for short MIS. And the motivation for that is shown here. This is a simple scene rendered using BRDF sampling only or light sampling only. And then here we are combining both of these techniques using MIS. And what you can see is that the two techniques individually have failure cases, whereas MIS looks nice everywhere. With BRDF sampling, we have an issue when we have a very rough surface and a small light source, because our specular lobe is quite wide, so we have a lot of random variation in our generated direction vectors here, and then the probability that they hit this small light source is quite small, so we get noise. With light sampling, we have the opposite problem. When we have this very large light sources and we generate random directions towards it, and we have a very smooth surface, then the probability that our random samples towards the light hit this very narrow specular lobe is small, so we again get noise. And with MIS, we can overcome both of this by combining both sampling strategies in a good way. The formula for that is relatively straightforward. The idea is we take one sample using BRDF sampling, so that has a density PB, and another sample using light sampling, which has a density PL. And then our MIS estimate for the integral is the function value for the BRDF sample divided by the sum of both densities evaluated for the BRDF sample plus the exact same thing using the light sample everywhere. So the idea here is that we compute the weights as if these samples were sampled using a combined sampling strategy. This is very similar to the single sample combination of strategies that we looked at before. The only difference is that we actually generate two samples here and use both of them. One pitfall when you want to implement MIS is that the density computation has to be working independently from the sampling, because here we are evaluating the BRDF density using here we are computing the BRDF density using the light sample, And here we are computing the light density using the BRDF sample. So you have to implement density evaluation separately from sampling, otherwise you can't use this. And now to actually put it all together, we need one last ingredient called next event estimation. Remember that this is how we construct our paths currently. We start at the camera, and then here we get our first vertex on a surface, and then we use a BRDF sample here to get the next vertex, and another BRDF sample to get the next vertex, and so forth. And this is how we recursively construct this path. But what we want to do now is that at every single path vertex, we take one additional random direction generated using the light sampling strategy. So for each vertex, we now will also trace a ray pointing directly towards one of our light sources. But the difference here is that these rays do not spawn complete paths. So we just trace this one ray here to the light source, and then that's it. We do not continue generating a path from this point. And of course, we would have to do this in the path tracing framework that we thought about thus far, and that's why we have to modify things a little bit using next event estimation. BRDF samples continue the path, light samples do not. To make this work, we take apart the integrand in the rendering equation into two separate terms, one for direct illumination and one for indirect illumination. Direct illumination, or direct radiance, means that the next vertex along our path gives us emitted radiance, meaning that the next vertex is on a light source. And then reflected radiance is simply everything else. So here we are just subtracting the direct radiance from the incoming radiance, and we call the remainder of that indirect radiance or reflected radiance. And now we look at the integral from the rendering equation, which of course contains the incoming radiance. Now we can take apart the incoming radiance into direct radiance and reflected radiance. And then we can take this apart further into two separate integrals, one containing only direct radiance and the other containing only reflected radiance. Now for these two integrals, we use two different Monte Carlo estimates. For the direct radiance, we use an MIS estimate that combines BRDF sampling and light sampling. And then, since the light sampling is only in this estimate, this means that we do not need the entire incoming radiance here, we only need the direct radiance. And because of that, we do not have to continue our path beyond this one ray. However, here we have reflected radiance, and that means that we do continue our path, but we do this using only the BRDF sample, so we only have one direction into which we continue the path. That's exactly what we wanted. Now, with that, I've told you about all the important sampling strategies in the renderer that I wrote for this lecture. And to conclude, I want to give a bit of an outlook into other interesting techniques that you can learn about, and also take some conclusions about path tracing. Previously, I mentioned that the technique I'm using to select one of the light sources doesn't scale very well. If you have hundreds or thousands of light sources, then you shouldn't be using this. And an option that you have in this case is called ReSTIR. And what this does is that it stores a few screen space buffers with information about the light samples that it used. And then it's accessing these buffers to figure out what light samples were good for neighboring pixels or for a point in a previous frame. And based on that, it can progressively improve the sampling distribution in a very nice and efficient way. Of course, all the results from a path tracer will have some amount of noise, and importance sampling will only diminish this noise, but it won't remove it completely. So it's always nice as sort of a last line of defense to have a denoiser that removes the remaining noise by simply blurring everything a bit. But blurring everything is maybe pushing it a bit too far, because you want to preserve contours in your images, and in general sharp features should be preserved as much as possible. So spatial temporal variance guided filtering is a denoiser that uses temporal coherence, it reuses previous frames, and it also blurs across pixels in a way that preserves features as much as possible. And then the last thing that's in general quite important when it comes to path tracing is stratification. What I explained was using mostly pseudo-random numbers, but it turns out that you can use other sequences of vectors of numbers that in certain ways behave like random numbers, but also have a few other nice properties. Namely, they are stratified, which means that certain regions in your domain will always get exactly one sample. So in some sense, these stratified random numbers are even more uniform than independent uniform random numbers. And then ideally, simply by exchanging the pseudo-random number generator for a generator of these stratified random numbers, you will get lower variance at the same sample count. Now to conclude, let's think about what we have gotten here. What is path tracing? Path tracing is a general framework that can handle all light transport. It's unbiased, which means that if we let it converge, we get the correct image, and in general we get the correct image plus some noise. So the errors of path tracing are very predictable. It's scalable because if you want higher quality, you can simply increase the sample count. It's parallelizable across samples and across pixels. It's efficient if you put in the effort to have good sampling strategies and good denoising and good stratification. And because of all of this, it's already the default in offline rendering, and I think it's the future of real-time rendering. But for that to happen, a few things are still needed. We need wider availability of good ray tracing hardware, especially in the consoles. We need better importance sampling for indirect light. I'll show an example of what I mean by that in a second. We need faster builds for acceleration structures to deal with the immensely complex scenes that we have in production these days. And that also requires level of detail, and in general there's still a lot of room for research here. But in addition to that, we also need a better understanding of path tracing principles among developers, because many problems already have good solutions, but the solutions are not so well known. And I hope with this lecture I've been able to contribute to that a bit. Now at this very last slide, let's look at render again. This is a scene that I like because we have very warm colors in here. We have a lot of indirect light because the light is coming in through the windows and then illuminating the ground, and from there it's spreading everywhere throughout this scene. The problem with that is that since indirect light from such small parts of the scene is so important here, one sample per pixel, this is still very noisy. It takes some time to converge. So this is what I meant just now when I said that we want better importance sampling for indirect light, and this is one of the fields of research where I think more work is needed. With that, I'm at the end. Thank you for your attention. I hope you enjoyed these 2 lectures, and if you want to keep learning more, I recommend that you look at the source code that's published alongside these lectures. And with that, I'm at the end. So thanks again, and have a nice day.